All right, let's jump straight into this explainer. We've got a seriously startling medical mystery to unpack today, one that actually starts right here on Earth, in an everyday emergency room, and rockets us all the way up to the International Space Station. We are going to look at a deadly secret hiding inside a super common illness, and how, weirdly enough, going to space might be exactly the key we need to cure it.
Just wrap your head around this number for a second. 1.2 million. That is the staggering, urgent number of emergency room visits for pneumonia in the U.S. every single year. Now, we usually think of pneumonia strictly as a lung problem, right? A severe respiratory infection, coughing, fever. But there's a hidden secondary threat that is arguably just as dangerous as the respiratory symptoms themselves.
And here is the curveball. Did you know pneumonia can actually cause fatal heart attacks? It's a shocking reality. The threat of this common infection totally doesn't stop at your lungs. It can trigger severe heart complications, arrhythmias, heart failure, and heart attacks that ultimately lead to death.
Seriously, the data is incredibly sobering. Roughly 1 in 5 people hospitalized with pneumonia will actually suffer a life-threatening cardiac event. And the danger doesn't magically vanish when you leave the hospital either. Those who survive face double the risk of experiencing some form of future heart failure. Doctors knew this was happening for a long time, but they just couldn't figure out exactly how the bacteria was pulling it off.
Which brings us to Section 1, unmasking the bacterial culprit. For years, this deadly connection was just a massive puzzle. Until recently, researchers at the University of Maryland School of Medicine and UAB started looking really closely at Streptococcus pneumoniae. This is the leading cause of community-acquired pneumonia, and they wanted to know exactly how it was breaking the human heart. The mechanism they found is literally like a microscopic lockpick. They identified a bacterial enzyme called ZMBB. This enzyme comes equipped with these very specific genetic segments called 5R domains. Essentially, these 5R domains are what help the bacteria survive, grow, and specifically invade human heart cells. So, here is how the microscopic invasion actually plays out. First, the bacteria breaks out of the lungs and enters the bloodstream. Then, those specific 5R domains act like tiny grappling hooks, attaching themselves directly to your heart cells. And finally, the bacteria invades the tissue, directly causing microlesions and cell death right inside the heart. And get this, researchers found that the more 5R domains a strain has, the more damage it does to the heart. They proved this definitively in lab tests. Mice infected with the normal pneumonia strain, they developed extensive heart microlesions and tissue death. But when scientists genetically knocked out that specific ZMPB gene, the resulting strain caused almost zero heart damage. The injury just virtually disappeared. It's an absolute game changer.
Moving right along to Section 2, spaceflight and accelerated aging. Okay, so we found the culprit. The problem is, studying how it attacks the heart down here on Earth is incredibly slow. To really decode this mystery, scientists needed to hit the fast-forward button on the biological clock. And for that, they turned to the ultimate extreme laboratory, space.
Think about what an astronaut goes through. They experience multiple massive hits to their system in microgravity. You lose that normal gravity-driven pressure, which causes rapid fluid shifts toward the head. And because of this extreme environment, astronauts deal with cardiac atrophy, intense oxidative stress, and even a heightened risk of arrhythmias.
And NASA hasn't just been guessing about this. They've been rigorously monitoring this cardiovascular deconditioning for well over 60 years. We're talking submaximal exercise tests on Mercury back in '61, plasma volume checks on Gemini, all the way to continuous long-term monitoring on the ISS today. They've built an unbelievable multi-decade baseline of data on how the human heart degrades under extreme stress. And all this research led to a totally mind-blowing paradox. Are you ready for this? Just 6 months of spaceflight perfectly mimics 10 years of natural physiological heart aging on Earth. Cardiac mass actually decreases, and arterial stiffness shoots up dramatically. Space is literally a fast-forward button for cardiovascular aging. Because it's not just the fluid shifts, right? Space radiation and microgravity trigger intense oxidative stress. They drive up inflammation and severely alter how cells handle calcium. It creates this perfect, highly vulnerable aged environment, which is exactly what you need to study how diseases attack a weakened heart. Which perfectly tees up Section 3, the ultimate extreme laboratory.
This accelerated aging sets the stage for what is happening right now aboard the ISS, where Expedition 74 astronauts are running a groundbreaking investigation called MVP Cell 09. Now, this sounds like a sci-fi movie plot twist, but zero gravity actually makes bacteria way more aggressive. Down on Earth, bacteria have pretty normal, predictable behavior. But up in space, pneumonia-causing strains show enhanced drug resistance and increased disease severity. This hyper-aggressive behavior is actually a huge advantage because it makes it much easier for scientists to observe exactly how they attack. Dr. Palanyappan Sethu summed it up perfectly. He noted that by intentionally exacerbating the infection on stem cell-derived hearts on its ship up in space, they anticipate a really clear separation between the infection and control groups. In that extreme environment, those subtle, deadly mechanisms, like our ZMBB enzyme, they stop being subtle. They become glaringly obvious. So the ISS isn't just a platform for telescopes, it's a totally unique biological lab. It completely strips away gravity-based variables, accelerates those cardiac aging models, and amplifies bacterial virulence. Basically, it lets us isolate the ZMPB enzyme's attack profile on advanced 3D-engineered heart tissues without any earthly distractions getting in the way of the data. Section 4. Protecting hearts on Earth. So why does all this orbital research actually matter for those of us keeping our feet firmly planted on the ground? Dr. Carlos J. Orihuela hits the nail on the head here. He says the hope is that by understanding these molecular fingerprints, we can better protect patients from heart damage during a pneumonia illness. By decoding these fingerprints in orbit, doctors are going to be able to use simple genetic tests to spot high-risk, FIVAR domain-equipped strains the absolute minute a patient rolls into the ER. The real-world ripple effects here are just massive. This space-based research could lead directly to targeted drug therapies designed specifically to block the ZMPB enzyme. We are looking at new, specialized vaccines, better early cardiac monitoring, and ultimately saving millions of people from unexpected secondary heart failure. Plus, it keeps our astronauts' hearts healthy for deep space exploration. So will the cure for Earth's most common ailments be found among the stars? It's a breathtaking thought, isn't it? By merging everyday emergency room data with the extreme laboratory of the ISS, we're literally cracking the code on a deadly medical mystery. It really makes you wonder what other incredible medical miracles are just waiting to be unlocked up there in microgravity. Thanks for joining me for this explainer, and definitely keep staying curious.